Okay, so the change in energy on the system is equal to the work done. So we looked at the change in energy. Now what about the work? Well, the system is not closed. That is because there is energy transfer to the system. Work is done on the system. So just clear that out. So if this is the fluid, okay, there's that fluid. On the left hand side we have a force applied to the right, okay, just as it's shown here, and on the top side, the right side, we have a force applied to the left. Where does this force come from? It comes from the fluid over here that is applying a force to the right to accelerate it, and the fluid over here is experiencing a force from the surrounding fluid to the left. Okay, so we have a F1 and we have F2, but because these points are displacing, there is a delta X. Okay, right there. There's a delta X over there and a delta X. Both of them are going to the right. Okay, so because there's a force and a displacement along the line of action of the force, we will have work over here, positive work, and here we will have negative work because we're having a force that is in the opposite direction of the displacement of the fluid. Okay, so that's exactly what I'm saying here. Work 1, which is on the bottom right there, is the force force 1 times delta x1, and this force 1, if we relate it to pressures, becomes pressure at 1 times the cross-sectional area. Okay, and this delta x, if we relate it to speeds, becomes the speed times delta t. Okay, so your work is pressure, area, speed, delta t. So that's work 1. Work 2 is similar. It is pressure, area, speed, delta t, but it's negative because it's in the opposite direction. So the total work done on the system is this. Okay. So, but what about, let's look at this over here, AV delta T. Because of equation 1824, if you remember, we had area 1, V1. This is not volume, it's speed, is area 2, speed 2. Remember, that's called your continuity equation. If we simply multiply that by the time, right, that gives us volume. Remember that AV, your volume flow rate was AV, right, which was meters cubed per second. So if we multiply this by delta T on both sides, we're basically multiplying by time, okay, and we're getting the total volume. So this AV delta T is the volume of the mass of fluid that flows into or out of the section. Okay, so keep that AV delta T. But we also know that volume is mass over density. Volume is mass over density. So if we say this equals that, right, we have mass over density is AV delta T. And if we substitute this into this equation over here, we will have this gets replaced by m over rho, and this gets replaced also by m over rho. So we have the work done. Work done is now in terms of the mass, the density, and the pressures. The work done is in terms of the pressures. So remember, delta E is work. Delta E on the left hand side is your change in kinetic energy. Change in potential energy is equal to a function of the difference of your pressures between point 1 and point 2. Okay, Then if we take this guy and we multiply, we divide by m everywhere, okay, then all of these cancel out, and if we multiply by rho, okay, we will get this. This is Bernoulli's equation, okay, pressure at 1 plus rho gy 1 plus half rho v1 squared, and then it's the same on the right hand side but at a different point. So notice that we used to have this equation for hydrostatics. Rho gy1 is equal to P2 plus rho gy2. Do you recall this? I think it was equation 18.6. This is for hydrostatics. But now we've introduced a kinetic term into this equation, and this is Bernoulli's equation. So this forms the foundation for hydrodynamics of incompressible fluids. This was for hydrostatics, right? Hydrostatics, but if we're now including these dynamic terms, they're now called hydrodynamics of incompressible fluids. Okay, so let's look at just some ideas here. First of all, this P plus rho gy plus half rho v squared is the same at different locations in a flow stream. Okay, just the same as this quantity here was the same at any point, at any depth, in a stationary fluid. This quantity is the same at different locations in a flow stream. Now let's consider again what happens if velocity is 0 everywhere. Then this equation simply becomes this equation, right? This equation, if the velocity is 0, then we just are brought back to equation 18.6. If another situation is, what if the flow is at the same height between points 1 and 2? Then these two are the same. They will just cancel out, and we'll be left with P1 plus the pressures and the dynamic components. Does that make sense? And of course, if it's not moving and at the same height, then P1 is simply P2. Right? So if there's point 1 and point 2 and it's stationary or static, then the pressures at point 1 and point 2 are going to be the same because they're at the same height. Okay, so make sure that you can understand how this equation works. However, okay, so here, if it is flowing and you're at the same height, then this quantity on the left must equal this quantity on the right. So if your velocity 2 is, say, higher than velocity 1, then because these terms are equal, your pressure 2 must be lower than pressure 1. Okay? Alright, cheers.